In a previous lecture, I very briefly kind of gave a very small overview of molecular orbital theory in conjunction with valence bond theory. And so I want to dive a little bit deeper into molecular orbital theory. And I'm not going to go like super deep because it is very, very complex. And it's to go, really in depth is kind of outside the scale of general chemistry. But molecular orbital theory helps us describe real bonding. And as I said earlier in our lecture, the one of the main differences between molecular orbital theory and valence bond theory is that molecular orbitals belong to the entire molecule. In valence bond theory, it basically says that the electrons in a bond are localized between two atoms, and that's where they stay. Molecular orbital theory gives a way to describe how those electrons could be delocalized, so to speak, across multiple atoms or an entire molecule. And this is kind of like hybridization in that we're mixing orbitals. And so what we're going to do is we're going to be taking atomic orbitals and mixing them up to become molecular orbitals. And one of the reasons why we don't go super in depth in general chemistry is that you really need a lot of strong computational power for pretty much everything except really simple, very small molecules. When you start adding even three or four or five atoms to it, the computational power needed, it would take, hours and even days for someone, for a human to try to calculate everything. And so computers are necessary because every time you add just one atom, you're adding multiple interactions between the rest of the atoms. And so this is why we're going to kind of keep it very simple. I'm just going to look at how we describe diatomic elements. And so let's start with just the simplest one, hydrogen, H2. Now what we're going to do is we're going to take the atomic orbital of one hydrogen. So that's in a 1s. It's got its one electron. And we're going to merge it with the atomic orbital, the 1s orbital of the other hydrogen atom. Now, like hybridization, however many orbitals you put in, that's how many you get out. And so when these two orbitals mix to make a molecular orbital, they can either interact constructively, much like a wave. This is why another kind of reference to electrons having wave properties. They can interact constructively to give an orbital that's lower in energy. We call that a bonding orbital. So remember this symbol sigma back in our bonding discussion of making sigma bonds. So if it interacts constructively, then you get a lower energy orbital. If it interacts destructively, you get a higher energy molecular orbital. And we still use the symbol sigma, but we put a star here. And what the star means, and this will be true for any molecular orbital, if you see a star, that means it's an anti-bonding molecular orbital. No star means bonding molecular orbital. So just like orbital diagrams or electron configurations, we're going to start filling up these orbitals. So I have two electrons to deal with, one from one hydrogen, one from the other. And so I'm going to put them both in that lower energy. Now, what I can do with this is I can calculate the bond order, and that will help me determine, does H2 really exist? Does that bond between two hydrogen atoms exist? So to find bond order in this manner, it's the number of electrons in the bonding molecular orbitals minus the number of electrons in the anti-bonding molecular orbitals divided by 2. So for hydrogen, for H2, there's 2 electrons in the bonding molecular orbital and none in the antibonding. So that antibonding orbital is empty. I divide by 2, that tells me there is a bond order of 1. I should have a single bond between hydrogen atoms, and that's the Lewis structure for hydrogen. Now, let's contrast this with another example. Let's look at diatomic helium. Now, if you remember from a previous lecture, you're like, wait a second, that wasn't one of those 7 you told us to memorize. Exactly. Let's see if molecular orbital theory can confirm if diatomic helium actually exists. So let's start with one helium atom, and it's got both of its electrons in a 1s orbital. And let's show what happens when it interacts with the atomic orbital of a second helium atom. And again, if they interact constructively, you get a lower energy bonding molecular orbital. If they interact destructively, you get a much higher energy anti-bonding molecular orbital. So let's take those 4 electrons and put them into our molecular orbitals. So I can put 2 here, and that's full. Now I got to go up here. So now let's find the bond order. So I'm going to take the number of electrons in the bonding molecular orbitals minus the number of electrons in the antibonding molecular orbitals. And then divide by 2, notice that comes out to an answer of 0. And molecular orbital theory confirms what we know about helium. Helium is not diatomic. He2 doesn't exist. Okay, helium does not bond to itself. All right, let's get a little more complex and look at oxygen. Now, this diagram on the left, I want to kind of demonstrate a little bit because we just been talking about s orbitals. So let's go into atoms that go into the p block. How do we handle that? So we have like a 1s, our 1s orbitals here, and those form the bonding and anti-bonding molecular orbitals. Then we go to the 2s. And again, notice we still have our bonding and anti-bonding molecular orbitals. Then what does the p subshell look like when they merge to make molecular orbitals? Well, so when you start getting into the p subshell, you still have your sigma bonding molecular orbitals. Now you have your pi bonding molecular orbitals. And they kind of have their, I guess, for lack of a better word, antithesis. There's the anti-bonding pi molecular orbitals and the anti-bonding sigma molecular orbitals. Notice the difference. I mean, this is something I really want to highlight here because we haven't looked at these computer-generated diagrams before. Look at the sigma bonding molecular orbitals. Notice how everything here is overlapping. And if you look at the anti-bonding ones, notice how there isn't a complete overlap. That's that destructive interference that I was talking about. And we could do the same thing for looking at the pi bonding and anti-bonding. If you look at the pi bonding molecular orbitals, notice how there's a really good overlap of those unhybridized p orbitals. But if we look at the anti-bonding, it's kind of easier to see on this one on the right. There isn't a complete overlap. That's why they're higher in energy. It's much more energetically favorable for there to be a lot more overlap. So now let's take a look at oxygen. Okay, so we know oxygen is diatomic. We're going to fill up this molecular orbital diagram. In order to do that, we need to know how many electrons are in O2. Each oxygen atom has 6 electrons, so that's a total of 12. Okay, so I'm going to start filling up those 12 electrons. I'm not going to worry about the atomic orbitals. I'm just going to start putting in my 12 electrons here. Oh, yeah. Okay, so 1, 2, 3, 4, and then 5, 6. I'm going to half fill these P first, 7, 8, and then 9, 10, and then I'm going to half fill these 11, 12. All right, and so now we're going to go through our calculation again to find bond order. All right, so I'm going to find the number of bonding orbitals. I'm sorry, bonding electrons. So there's 2, 4, 6, 8. So 8 bonding electrons. And then how many anti-bonding? There's 2, 3, and 4. So 4 anti-bonding electrons. Divide by 2, that's the solution to that is 2, which verifies the bond order that we know oxygen to have. We've drawn the Lewis structure of oxygen. Oxygen has a double bond between its 2 atoms. And so that does verify, number one, that oxygen does bond to itself, and it does so in a um, in a double bond fashion. Now, in conjunction with this, we're going to use molecular orbital theory to describe some properties of diatomic elements. And one of these properties we're going to be looking at is paramagnetic versus diamagnetic. Now, what does that mean? If something's paramagnetic, the result of that is it's attracted by magnetic fields. If something is diamagnetic, the result is it's repelled by magnetic fields. Now, the way that we can determine if something is paramagnetic or diamagnetic is we look at the electrons. A paramagnetic substance will have at least one unpaired electron. A diamagnetic substance, all the electrons are paired. All right, we're going to look at oxygen again. If I were to draw the Lewis structure of oxygen, everything looks paired up, right? Like all the lone pairs are paired up and all the bonding electrons, they're all paired up. So oxygen should be diamagnetic, right? It looks paired. But we know experimentally, oxygen is paramagnetic. In fact, look at the picture on the right, this over here. This is demonstrating, this is liquid oxygen, so oxygen that's been supercooled, and it's being poured between 2 magnets. And you can kind of see right here in the middle that oxygen is being held in place, that liquid oxygen Oxygen is being held in place by those two magnets. It's attracted to those magnetic fields. So the Lewis structure isn't really giving us the correct picture. And that's where we're going to look at the molecular orbitals. So I just did the molecular orbital diagram on the previous page. I'll do it again here. So again, I got to place 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And what do you notice about the electrons? Especially these right here. Those are unpaired electrons. And so you can see that molecular orbital theory explains or helps us explain this real world evidence that oxygen is paramagnetic. It's attracted to magnetic fields. Now, finally, let's do this for nitrogen. So N2 has 10 valence electrons. Each nitrogen has 5 valence electrons. So one nitrogen, 5 valence electrons. And again, we could do this for the whole structure, but we're just concerned with the valence shell. Okay, so if I put 5 electrons in here for nitrogen, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. I'm going to put those now in the molecular orbitals. So 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, first of all, what do we notice about the electrons in terms of paired or unpaired? Are there any unpaired electrons? All electrons are paired. So that means nitrogen is diamagnetic. It is not attracted to magnetic fields. It's actually repelled by magnetic fields. A lot of times that repulsion is so small that it's really not noticeable unless you have like really powerful magnets. Now, the other thing we can do to round this out is let's calculate the bond order for oxygen. I'm sorry, nitrogen. In the past, we have done the Lewis structure for nitrogen and saw that it should have a triple bond between it. So let's see if the bond order verifies that. So I have 2 bonding electrons, 3, 4, 5, 6, 7, 8. So electrons in the bonding molecular orbitals, that's 8. And then I'm going to subtract the number of anti-bonding electrons, and that's there for in the anti-bonding 2s. So I only have 2 of them. And then I subtract by 2. That comes out to a bond order of 3. So hopefully this helps with diving a little bit deeper into molecular orbital theory. As far as what you'll see, say, on an exam, is I'd like you to be able to fill out a molecular orbital diagram like we've done here for something very simple. So we've done like nitrogen or oxygen, or maybe I might ask you, does a particular bond exist between 2 atoms? We saw that with when we were looking at hydrogen compared to helium. We were able to determine if H2 exists, and then we were able to determine that He2, helium-2, does not exist. So I just want you to be able to use these molecular orbital diagrams, be able to fill them in, and number 1, calculate bond order. Number 2, be able to determine if that diatomic element will exist. And then number 3, be able to determine if that element, or that diatomic molecule, I should say, is paramagnetic or diamagnetic based on are there paired or unpaired electrons.